Okay, hey everyone, welcome to session 2. So last session we were discussing supervised learning and how to modify trained models that came from another domain into the domain that you're working with and ensuring that they adapt well to that domain. It's a challenging topic, but hopefully the code that you have there is something fun to play around with and you learn a thing or two. This week in session 2, we're going to talk about self-supervised learning, and we're going to use this in the context of anomaly detection with respect to categorical variables. All right, so let's get started. Okay, so anomaly detection, I'm sure a lot of you have done some form of algorithm in this in the past. Fairly useful algorithm to have in your tool set. Typically, you're just looking at unusual events that are occurring outside of a distribution. So you can see here on the right, you've got, this is just data that's generated from a multi-nomial distribution. And we have a couple of anomalous events just to the right of it. So these events are generally going to be driven by continuous features. So for example, you can think of fraud detection where you might be looking at, well, okay, this transaction, how much did it cost on average over the past X many weeks? How much has this person spent maybe at this store? When was the last time that they made a transaction? Like how many hours has it been since their last transaction? These kind of things that you could maybe bring in, whatever features you might think are relevant, but all of these are continuous features, and all of these features are in a space where you can relate one feature to another. You can say this number is bigger than that number, or smaller than this number, or these numbers combined are greater than these numbers combined. So you're able to develop a metric space to compare values and essentially find outliers so that you can alert whoever needs to be alerted and then go and investigate. So that's all well and good. There's various different algorithms you can use. K-nearest neighbors, isolation forests seem to be very popular these days. One-class SVMs, autoencoders, you can use them in that you're compressing the information. You're assuming all of the information you have is real or is non-anomalous. It's normal. You compress that information down and then reconstruct it. In autoencoders, to create an autoencoder, the loss function, the loss function is really looking at the reconstruction loss. So how similar does your input look to the output? A trained autoencoder, then the output is going to look very similar to the input. So if something is anomalous, then the reconstruction loss should be quite high because it's out of the distribution and the neural network has never seen it before. Another approach that you can use is cluster analysis, where you try to cluster things into whatever bins you want, and if anything is not fitting into whatever pigeonhole you want to put it in, then maybe we should investigate this as well. So yeah, as I was going to say, this is all well and good. This is always in scenarios where you have numerical data, things are continuous, things are a lot easier to compare and contrast values and say, this is weird, this is normal. How do you do this with categorical data? How do you look at anomalous events? So events are often containing categorical data. So you can look here at this little diagram here. We've got an event where a user is logging on with a particular device from a particular IP address on a particular day at a specific time of day to a specific service or server. So this is typically these values are categorical. There's not going to be a metric space allowing you to compare. So you can't say database 1 is greater than database 0. Even if 1 is greater than 0, it doesn't actually mean anything to compare one of these two categorical things, right? There's no metric that you can use to say this is greater than this or less than that or whatever. Even if it's a credit card number, obviously this is not something that we can compare these things to. And I think humans are very bad at doing this in general, particularly when you've got something that's very highly cardinal. So, you know, if there's only two possible values and you look at something that's very unusual in those two values, maybe, I don't know, like it's a fraudulent transaction, but no, that's probably a bad idea. But an alien and a human, for example, you're going to have lots of humans in a room, and if an alien walked in, well, that would be anomalous. But if there's a lot of high cardinality of different possible events that can happen, it becomes very difficult for humans to understand what is unusual and what is normal. It becomes even more difficult when you add in combinations of features and you're trying to say, well, what combination and what permutation is unusual here? In fact, in this example here, the only two features here that are actually something that we can create a metric space on are the days and the time. And these are things that get beaten over the head of us every day because we see the sunset and sunrise, we see the seasons come and go. So we're very used to knowing, well, okay, it's very cold in the winter. So if it was 30 degrees in December, you would be concerned. But typically, for a lot of event data, it's categorical. We can't actually say this is an unusual thing compared to all of the other features. Okay, so how do we embed these values into some kind of space that you can then compare and contrast these values? This would be really easy if you have supervised learning. So if you have labels and saying like this is normal, this is abnormal, like it's fraud, for example, then this is pretty easy to do. So you just train the supervised learning model. Then you can look at, say, the last layer before your classifier, and you've now got a nice in high dimensional space that you can embed the normal events and the abnormal events, and you know exactly what you're looking at. But if you don't have labels, this is going to be a lot more difficult. So what if we made our own labels? Maybe there's something we can do so that we're able to ensure that we have understood the true distribution of what normal data should look like. And then if we've understood that, then we can find things that are going to be out of distribution. Okay, so this brings us to self-supervised learning. All right, and so what is self-supervised learning, you may ask? Well, it's supervised learning without labels, without explicit labels. So somebody hands you a data set, here are all the X's, and oh, by the way, here are all of the Y's, like MNIST, so we have our labels to go with our data. That's just regular old supervised learning. If somebody hands you a data set but says, we don't have any labels here for you, well, you got to make your own. So the labels are going to be created from the data itself. Then you just have to have the model perform a certain task according to these labels. These tasks can vary according to the domain that you're in, what you're trying to achieve. But it's a very ingenious way to get around the fact that you often do not have labeled data. So an example is that you can apply this, an example of a domain that you can apply this to are images. So you could ask a classifier to say, well, you train it with regular images, and then you also train it with images that have been rotated by some degree. And you asked a classifier to say, well, what degree did it rotate by? 45 degrees, 90 degrees, 130 degrees. In learning the angle at which an image has been rotated, it has to learn, well, what is the true angle? And it has to learn, well, what does it normally look like? That if face had been rotated 180 degrees, well, it's not normal that the eyeballs are below the nose, that kind of thing. You can also learn the global structure. So maybe patches of images are fed in and it has to make a decision about these patches. We're going to talk about that a little bit later. You can apply this to sequences. So maybe you have a sequence of points. It could be video frames. It could be a song. It could be earthquake data. It could be whatever you want. But if you take a point in that sequence and you move it to the end of the distribution or to the start or somewhere else in the distribution, and then have a classifier say, well, which of these is a true sequence? One is real, one's fake. Classify for me. You can also do forward versus backwards classification. So did this video play in the forward direction or did it play in the backwards direction? Did this sequence of events occur this way or did it occur the other way? You can also apply it to text. So we're going to talk a little bit about word embeddings, which is a great example of self-supervised learning. BERT is another example where you kind of have sentence embeddings as well. So I think the lesson here is that any kind of domain that you're in, any kind of data that you have, if you think about the problem that you're trying to solve, maybe there's a way that you can create a challenging enough counterexample so that the classifier or the model that you're trying to train is able to learn what is normal and what is going to be abnormal here. Okay. Oh, and of course, so it can be applied to tabular data, which is what we're going to be talking about today. Okay. So here's an example of self-supervised learning with images. In this image of a cat, you have to determine the relative positions of patches from the image. So given this central patch of the cat's face, you have its left ear. You have to decide where in this image is the ear going to be. So you've got 8 possible candidates. And so you can do this many times for just one image alone, and you can do this for many, many images. And eventually it'll start learning the global structure that occurs around a cat's face or a car or a building or whatever it is that you're trying to get the algorithm to classify or understand the representation of. So this was from Unsupervised Visual Representation Learning by Context Prediction, ICCV 2015. You should note that there's a large gap between the patches here. This was to ensure that the algorithm didn't cheat by learning that, okay, there was this little line in here and this little line here kind of matches up with it. Much the same way that we might, build a jigsaw. If that jigsaw has thousands and thousands of pieces, it's very hard for you to say, well, this clearly is in the upper third of this person's face, so I'm going to put it there. But you can maybe say, well, there's this line, this squiggly line that goes here, and this piece also has that squiggly line, and also the hole on the dangly bit, they seem to align pretty well, so that's how that goes together. So much the same way that we would build a jigsaw, this algorithm would learn how to do that. So you need to obfuscate portions of the data to ensure that it's not cheating. So in concept, it's easy to do self-supervised learning, but in practice, you have to be very careful in making sure that you're not providing any kind of outs for the model. Although as you train these things, if it's learning very easily, but then it isn't transferring well, then it's probably clear that there's something happening and that the model is probably cheating then, and you need to reevaluate what you need to do. Okay, so another example would be what I was talking about earlier, where you're talking about temporal order verification. So given a video, you might look at, these are different frames from that video. And so here we have somebody playing baseball. And so this guy is, he's throwing a pitch. And we can see that we inject a frame from earlier in the feed into the middle of this sequence, then it's going to be a temporally incorrect order. And the model has to distinguish between, was this real or is it fake? So here are some examples of positive tuples of somebody bowling, and again, somebody pitching, somebody bungee jump. Looks like they're just diving. Different sports, but the idea here is that you're going to end up learning how to do, the model is going to end up learning how to do scene classification. Like this is somebody running down a track. This is somebody eating cereal. It could be anything that is, it essentially is learning the intrinsic physics that occurs. It's learning the intrinsic behavior that people have when they're doing certain things. And all of this is coming from unlabeled data, which is really, really cool. Okay, so probably the most famous example of self-supervised learning are word embeddings. So what are word embeddings? Well, the concept is pretty simple. It's just the famous quote is that a word is characterized by the company that it keeps. So essentially, you're trying to learn the meaning of a word or have a model learn the meaning of a word by using the context that surrounds that word. So the end result is that you get a vector representation of these words that are a high dimensional space in which you can embed these words and you can relate them to each other. So examples of word embeddings are word2vec or glove. And in this cartoon here, we've got 5 different points in this 3D space, which is laughably small compared to the word2vec space of, say, 300 dimensions. But you can get the concept here, where man, woman, and child are all very similar to each other because they're similar concepts. They're all humans, right? But ocean, okay, maybe it's a concept of nature, but it's a good bit further away from us. And likewise, fork is going to be further away from ocean and people because it's not natural, it's man-made. It's going to live over in that portion of space. So the idea is that you end up learning words, the meaning of these words to some degree, that they end up living near each other. So maybe over here is a cloud of words that correspond to finance. Over here is a cloud of words that corresponds to biology. Over here is a term like a cloud of words that corresponds to video games. It could be anything, but the idea is that it learns based on context, this word is similar to this. You can learn things like this is a noun, this is a verb. Obviously, these things are not explicitly learned, but you can infer that this has been learned by analyzing the outputs and saying like, okay, well, there's relationships that have been discovered here. So an example of a relationship that you can have is if you have the word vector from man, and then you add the word vector of royal to man, you can end up getting towards the word vector to king. And then if you add the word vector of female, then you get over to queen. And if you subtract royal from queen, you can get to woman. So this whole form of vector addition is very clear that there's some space that has actually been learned. Now, it's not a perfect space, but these word embeddings are what powers a lot of natural language processing these days, and it's a very, very powerful technique to use. And it's something that we're going to borrow today for anomaly detection. So how do word embeddings work? Well, like we said, it's all about, for a given word, looking at the context around it. So, or for a given context, what is the word that goes in it? So maybe a classifier has to decide what is the word that goes in this sentence. The blank sat on the mat. Okay. So you've heard this thousands of times, so you know that it's going to be the cat that sat on the mat. The classifier, however, has no clue. It could be anything. So it has to go through all the possibilities. The planet sat on the map. The cookie sat on the map. And it's essentially going to have to go through every single last possible word in its vocabulary to decide. Okay, so you could build a classifier with V classes where V is the size of your vocabulary. But given the tens of thousands of words in the English language, this is not exactly going to be a very simple task. Your softmax is going to look very, very ugly because you are trying to normalize this into a probability distribution, and it's going to be thousands and thousands and thousands and thousands of very, very small values that, you know, given whatever kind of precision error you're going to have, it's just going to be noise, and it's going to be very difficult to train this properly. So maybe there's actually a better way than trying to get a classifier to guess what word goes in there out of all of the possible words. Maybe we just give it an easier choice. So instead of having it to guess every possible word, we just give it the true word, and we also give it a fake word. So in this case, the classifier, it has to decide, is it the cat that's out on the mat, or is it the planet that's out on the mat? And maybe we give lots of examples, not just for the cat. So we could say not only the planet, but also different words like the chair, or the quickly, or the hungry, or the large. So they don't have to be nouns. They could be any possible word. The is, the was, any word in the English language, not even in the English language if you wanted, although that would be a bad idea. And we'll see why in a second. But you can pick any word you want. The idea being the more words that you have that are not real or do not fit in this context versus the one that does fit in this context, the better the algorithm is going to learn. But you've massively reduced the complexity of your problem in trying to predict tens of thousands of different possible values to just, well, your softmax now really only has one or two or n possible values. Okay. So you should make sure that you're actually using a real word, because you could just give it some random string of characters, or a French word, or, you know, a word from another language, any other language besides English, and it's going to be very easy for the model to classify this. It's going to look at this and say, well, that doesn't follow all the usual rules of starts with, you know, a consonant and then followed by a vowel and then maybe ends with a consonant or whatever. And I've never seen a percentage sign in a word before, so this is clearly not a word. Therefore, I'm going to go with cat sat on the mat. So this is a really poor example of a negative sample. You would want to make sure that your negative samples are actually challenging enough for the classifier. Okay.